Good afternoon, dear colleagues. My name is Alexandra Yeremenko, Kharkiv National University of Radio Electronics. I present the Department of Infocommunication Engineering named after Professor Volodymyr Popovsky. Today I present the speech on topic Investigation of the Multicast Routing Model with support of traffic engineering and its application in software-defined networking. The development of technological solutions gave rise to the emergence of future networks, the concept of which is based on existing networks demanding new solutions for managing and adapting current services, self-organization and self-regulation to meet new communication requirements, especially for mobile users. In particular, effective management capabilities are designed to ensure the rapid adaptation of operators and service providers in cases where current services do not involve an excessive cost increase. One of the main trends in developing modern communication networks is expanding the services provided to users. However, the share of multimedia services is constantly growing over time, which requires continuous improvement of technological means for quality of service QoS ensuring, the main of which are routing protocols. It's advisable to use multicast routing protocols for most multimedia applications, including IPTV, distance learning, online radio, video on demand, and video conferencing. The current work aims to improve the multicast routing model using the principles of traffic engineering associated with providing a network link load balancing in general, which helps to improve the quality of service. Currently, modern networks use a variety of multicast routing protocols, which differ in application range. The general classification of IP and SDN multicast routing protocols and algorithms is shown on this slide. Thus, the Border Gateway Multicast Routing Protocol, BGMP, belongs to the class of external gateway protocols, inter-domain routing. At the same time, multiple application-independent multicast routing protocols are used at the level of internal gateway intra-domain solutions. The dense mode protocols should be used in networks with the high node connectivity, and the sparse mode ones should be used in networks with the sparse structure. In turn, some protocols can be distinguished for networks where nodes can be moving objects. But these protocols have one common feature. They calculate a multicast route by constructing a spanning tree. It is the backbone tree that connects all nodes included in the multicast group. A characteristic feature of minimum spanning tree search algorithms is the acceptable computational complexity of the calculations. They are almost perfect for technological solutions that involve the transmission of individual, relatively small volume messages. However, in providing multimedia services, applying graph models and combinatorial algorithms can reduce network efficiency because they do not explicitly consider the parameters of high-intensity multimedia flows and bandwidths of communication links, leading to network overload. Therefore, considering current trends in developing the SDN multicast routing algorithms, the following improvement of the flow-based multicast routing model is proposed. Within the multicast routing mathematical model, the following notations are used. Network graph G, the corresponding set of vertices, modern network routers, and a set of arcs, modern network links. Number of network links and nodes. Capacity is associated with every link, a set of flows circulating in the network. With every flow, there's associated average packet rate intensity measured in packets per second. Source node for packets of a particular flow, a set of destination nodes, which is used for obtaining order of multicast routing. Total number of destination nodes. Routing variables determining the order of multicast routing. Circuits within the graph G, a set of arcs involving in every circuit, power of set, which corresponds to every circuit. C is the routing metric which characterizes the basic parameters of the network link, and control variable alpha, which characterizes the upper bound of the network link's utilization. Within the multicast routing mathematical model, the following constraints and conditions are adopted: a single pass routing strategy, conditions for preventing network overload, flow conservation conditions for multicast routing, for source node, for set of destination nodes, and for each transit node, conditions for prevent local loops occurrence. Optimality criterion is the metric-based functions that should be minimized, where C is the routing metric which characterizes the link parameters and quantifies the conditional cost of its use in a multicast pass. For example, if C is equal to 1, the network will use the RIP protocol metric, number of hops. When C is equal to 10 in the power of 7 divided by link capacity, the network routing will be organized similar to the metrics of IGRP, EIGRP protocols. The application of this criterion with conditions in multicast routing problem solving makes it possible to formulate a technological problem as optimization. Moreover, the linearity of the criterion, constraints and conditions allows using efficient methods of integer linear programming or approximate heuristic methods to obtain the desired solutions from the computational point of view. Next, improvement of a mathematical model of multicast routing using principles of traffic engineering technology is proposed. The following changed expressions modify link overload preventing conditions to provide a link resource balance utilization under the traffic engineering approach. Here, alpha is the link's utilization upper bound and additional control variable. The constraint is imposed on alpha considering its physical meaning. Then the updated optimality criterion will be represented as minimization of this parameter alpha. The following slides are devoted to investigation of an improved multicast routing model in SDN. A multi-flow case was considered when, for example, two multicast flows were circulating in the network simultaneously. The source for both flows was the first router, and the destinations were determined as follows. For the first flow, it was third, fourth, and sixth routers, and for the second flow, second and sixth routers. The flow's intensities varied from 10 to 90 packets per second. During the simulation, the first multicast flow and second multicast flow routing trees have been obtained. However, within the second multicast flow routing tree, we can see inappropriate use of links between first and third routers and between second and third routers. Consequently, additional conditions in the proposed improved multicast routing model to prevent inefficient use of the link resource have been introduced. In accordance to condition 12, it was obtained the second multicast flow routing tree. Finally, the modeling results confirm the linear nature of the link utilization upper bound dependence on the flow's intensities that arrived at the network. Conclusion. The multicast routing model in the softwarized communication network, which belongs to the class of flow-based solutions, has been improved in the work. The model's novelty is the optimality criterion, which quantitatively corresponds to minimizing the most loaded link utilization to provide balanced network resources usage under the traffic engineering requirements. During the study, it was found that when applying optimality criterion, the communication links, the utilization of which did not critically affect the boundary value alpha, could be unreasonably used. Therefore, the model has been supplemented by conditions to prevent this situation. The implementation of the proposed model allows load balancing in the network, which transmits low-intensity multicast flows compared to the link's bandwidths. The model guarantees a linear growth of the link's utilization upper bound, which positively affects the quantitative values of the main quality of service indicators. Thank you for your attention.